Our third speaker of this, Aritra Sarkar, will present about visualizing quantum circuit probability. Please go ahead, Aritra.
Thank you, Marlo. Hope you are having a great day at the Quantum Science Days. I'll be presenting about our work on quantum circuit probability. I'm Aritra. I'm a postdoctoral researcher at QTech, part of the Delft University. And this work was done with my collaborators, Bao, Akash, and Tomal. So this work originally started in QIntern 2021. So that's almost 2 years back. And recently we got the work published. The name of the article is Visualizing Quantum Circuit Probabilities, Estimating Quantum State Complexity for Quantum Program Synthesis. But on today's talk, I'll be focusing more on the concepts behind this, and for the more fancy results, you can look at the article. So to start with, why are we even bothered about quantum state complexity? And that comes from the fact that we are working with quantum computers, which are basically evolving quantum states using unitary transformations. And when we are working with gate model quantum computing, this is basically done with local gates, which acts on a few qubits at a time, mostly in the nearest neighbor fashion. And this gives rise to some depth of the circuit, like which basically captures the notion of time, and a width of the circuit, which captures the notion of space. And this together, the space and time, is basically what's called as the quantum circuit complexity. So quantum circuit complexity has been studied from many different angles, and mostly it started off with things like high energy physics. But for today's talk, we'll be focusing more on a little bit more practical aspects of quantum computation, where this quantum circuit complexity, or how many gates are required to implement the circuit, gives us a notion of how efficient our implementation is of this particular unitary. So before we go into quantum circuit complexity specifically, we'll look at two other types of complexity, which are more widely studied. So let's come back to the idea of states in a classical systems. So states have states are based on what we observe in the world around us. And when we observe the same things over and over again, we take the statistics of what we are observing. And that gives us, and then if we divide it by the total number of observations that we have done so far, we basically get a kind of probability distributions of our observables. So let's say these are the different these are the different states that we observe in the world, and these are like the probability of observing them. It will be a super boring world if we see all the states with equal probabilities. There will be no way to predict what's going to happen next, and it'll be everything is kind of random. Fortunately, that's not how we see the world. So we see two differences. The first one is the states that we see in the world are not uniform, like they are not uniformly present. So we see certain kind of distributions. And this is captured by Shannon's information theory very well in the classical case. And that basically allows us to transmit informations very efficiently over a channel. The other difference is we see that states are basically related to each other. And that is basically captured by the computability model from Alan Turing, which states that we can make all the states out of a few simple ones. For example, if we have this primary pigments of orange, magenta, and cyan, we can mix them in different ways and get the other pigments or colors. So if you're a painter, you would know that. And then there will be some other states where we have to mix with more varied linear combinations of these building blocks. So these are two very different notions of how its states are actually not uniform and not related, but there are differences. So the first one, for example, doesn't tell us how is it impacting our notions of observing the world, while the second one just tells us that the states are non-uniform in the world. It doesn't tell us why. So these two fields are basically what's related with what's called as algorithmic information theory, which basically tells us that the states that we see with high probability are the simple ones. So those are the ones which has, for example, one color. The second highest ones are the ones with two colors, and the really complex ones we see with much less probability. So the more the complex a state is, less probably we see them with much less probability. And that helps us to understand how efficient our modeling of the world is. And this very widely used and forms the basis of artificial intelligence, in fact. So now we have two very different notions of complexity. The first one is what's called as statistical complexity, and that comes from Shannon's information theory. And the second one is called algorithmic complexity, which comes from this algorithmic information theory. So now we have these two different notions of complexity. And before we apply to the quantum world, we have to go across two very important differences. The first one is the difference between continuous and discrete. So what I showed in the previous slide is a discrete number of observations. We know that, for example, the difference between many types of infinities. So there are countable infinite sets, and then there are uncountable infinite sets. But each of these countable and uncountable infinities can be fairly well approximated among them. So this gives rise to two different approximations. The first one is continuous theories can be approximated or generalized. They can approximate or generalize a discrete set of observations. So this is widely, for example, used in statistical machine learning, where we have a much more easier definition of a curve, which generalizes our data set. But this has the problem that this is kind of an approximation, so it can lead to underfitting or overfitting. On the other hand, we have, if we are given an infinite number of discrete blocks, we can represent any continuous functions. This doesn't work so well in some systems, like if they are chaotic, but in most cases, even in quantum field theories, we can form what's called an effective field theory, where we don't care so much about the low precision values. Is the world ontologically continuous or discrete? That I'm going to leave for philosophers. If you're interested, you can look at things like Zeno's paradox. But quantum mechanics is a very weird mix of them. So on one hand, we have a continuous Hilbert space where we have a continuous choices over what quantum states or what quantum processes can exist in them, as well as what measurements we can do on that Hilbert space. But once we choose them, then we have a discrete set of independent observables that we can see, as well as the collapse state. Like based on the observables, we would have a discrete set of collapse state. So that's one difference. The second difference is once we take space as constant, so when we are discussing a specific number of qubits, we can count time in a discrete world by just counting the number of blocks. And in a continuous world, we can just assume time to be continuous, and we can count the time on a wall clock, for example. But even when we have an infinite number of processes in a quantum world, not all processes are kind of created equal. So that doesn't mean that they require the same amount of time. For example, the S gate is kind of takes half the time as an Z gate, or T gate takes half the time as an S gate. So these are nicely captured by what's called as quantum speed limits. And in the geometric formulation of quantum computing from Nielsen, you can think of this being a geodesic in some Riemannian space. And the length of the line kind of gives you a notion of how much time is going to take for implementing that particular quantum process. Of course, there's notions. These vary based on your notion of process distances. We are not going to go into that. And the second important difference with quantum is when we discretize it into our notions of operationally making a gate-based quantum computer. So then you have this curve, but we are basically discretizing it using a specific set of operations. And that is basically increasing the length of your line. So that is a notion of how long it's going to take. And the longer it's going to take, for example, if you're trying to do an quantum adiabatic evolution using QAOA, we basically discretize it in a way. So now it's basically taking longer time, which means that there more noise can seep into the system, but also most importantly, it takes additional time. So with these two changes, now we have continuous Hilbert space, but we have these choices. And then we have, once we choose, we have this discrete things that we can observe about the system. And this is basically what's called as ubiquity of quantum universality from Seth Lloyd, which means that it's very easy to create universal quantum systems. You can pick pretty much any set of quantum gates, and you can then implement universal quantum computation from it. So if that's a discrete set, we have a very nice algorithm from Solveig et al. And that gives you a compilation of what gates you need to run in a sequence to approximate your any unitary very well. Instead, if you have a continuous gate set, then you have something called as quantum Shannon decomposition, which again gives you an exact decomposition of any target unitary. But both of these kind of tell you that there will be, again, some states which will require an exponential number of gates. And that's what's called as quantum Kolmogorov complexity, that you can approximate very well the entire Nielsen geometry, but then there will be some pockets for which you will need an exponential number, which makes sense that, for example, if you are trying to approximate a real number with integers, decimal places, for some integers, you're going to need a very long representation. For example, if you want to perfectly represent pi, for example. So all these kind of runs back into the quantum speed limits and the geometric interpretation that there are many ways of discretizing this continuous space. And what we are interested more is in figuring out what universal, like we are trying to compare different kind of universality and which is good and which is bad. So again, not all universality is equal in terms of how much resource it takes. And this is basically quantum algorithmic information theory. Most of the theoretical work is done using quantum universal Turing machines, and we are exploring how to do it with quantum circuits. So this is the basic idea behind our implementation, where we choose a set of gates and some observables, and then we can do a combinatorial listing or enumeration of quantum programs which implements these different unitaries and measurements. And then if you have a cutoff of how long we have for doing the computation, which basically comes from the decoherence time of your quantum processor, then we can only reach specific places on the Hilbert space. So if we choose a very different set of basic gates and observables, again, having the same cutoff, it's very likely that we will reach very different places on the Hilbert space. There will be almost no overlap between the places that this gate set reaches and where the other gate set reaches. So we have a lot of choices when we're doing quantum computation, because we're choosing from an infinite number of processes and gate sets. Normally, we talk about qubits and the decoherence time, but also we need to consider the native gate sets, the connectivity between different qubits, measurements, and of course, since everything is subjective, we can think of gate sets which work very well for particular algorithms. So basically, what's an observer in quantum information theory are like the QPU manufacturers in the quantum world, and each of them has different pros and cons. For our evaluation, we looked at two different metrics. One is the expressibility, which is kind of the corresponding notion of computability, where we have an unbounded number of gates, and we can think of what all quantum states we can encode. And this falls back from the ubiquity of universality, that if we are given an unbounded number of gates, it's very likely that we'll be able to reach any quantum state possible. The second notion is more like interesting, where we have the notion of complexity, where we time bound the expressibility, and we see the sequence of gates that reaches specific states. And most of the results in our paper kind of looks like this, where we have this gate sets that we are working on, and then the number of qubits. And with increasing depth, so increasing limit on the time, what are the states that we can reach? So we have, for 4 qubits, we have 16 input states and 16 output states with measurements on the Z basis. So the first row is basically the expressibility, and the second row is the reachability. So it's kind of dividing by the total number of executing circuits. This is more like a heat map of where we can reach more. So if we sum them up, sum the lower ones up, that kind of gives you the total reachability of any quantum state from another 4-qubit quantum state, what's the probability of going there? So we did some more experiments on the paper. We looked at compare different kind of gate sets. For example, this is X plus Toffoli and the standard gate set. It's a little bit hard to see, but there are a lot of differences between them as well. We also did some experiments on different topologies in the IBM system. So over here, it's even harder to see directly from these. So we did kind of a difference graph where you can see that if we are looking at quantum algorithms which needs this kind of green evolutions, then it's better to run it on the L topology. While if it needs this pink transformations, then it's better to run on this particular T topology. So again, now we have this notion of experiments that we did. Let's connect it back to quantum state complexity. So what we saw previously, the reachability graphs, that is basically what's called as quantum state probability in the circuit model. So that's the notion that we defined in the article. And the full statistics, the full matrix, green matrix that we saw, that is what's called as the universal distribution, the correspondence of the universal distribution in the circuit model. And there's another notion which is already pretty well known from many different circles, from statistical mechanics to information theory, is once we have low complexity, that means we have a high probability, because complexity and probability are related as a negative law of the probability. So now we can kind of find correspondence between action and complexity, which was already done by Brown and Susskind. But we have a technique of estimating the complexity using the probability. So this is also very well known in the algorithmic information theory circle. Hector Zenel's group has done that for example, in bioinformatics and genomics. We are trying to do the same thing for quantum circuits, basically. And there's something called as a coding theorem from Leonid Levin. We are using that techniques in quantum circuit for determining or estimating quantum circuit complexity. And this works because Turing machines and circuit models are very similar to each other. And there are ways of approximating universal behavior on a family of quantum circuits. And this is how kind of the equation looks like. The graphic, what I showed in the graphical form, in the equational form, it is basically taking a statistics of how many of those circuits reach a particular quantum state S, divided by the total number of quantum circuits that can be expressed in that time frame. And if we take the negative log of that, we get an estimate of the circuit complexity, which is a very important metric, as we saw. So these things can be, like we started off on this journey by getting inspired by quantum artificial intelligence. So that's some work that I did during my PhD. It's called as a quantum knowledge seeking agent. And we were trying to move towards inferring causal models. That's also a very important feature of artificial intelligence systems. And also from a recent surge in geometric quantum machine learning and using tools from information geometry to do machine learning. That's some of the work that we are planning to do in the future. But right now, most of the work that we're doing is in quantum program synthesis. So that helps us to, for example, finding efficient gate sets. So if you have to compare two different gate sets, which gate set would I choose for a specific class of quantum algorithms if I'm given a choice of two different gate sets from two different QPU vendors? And how would I compile any arbitrary gate set to a specific quantum hardware? Also, we are trying to find ways from novelty search that's also well known in the genetic programming community. We are trying to use those for building new quantum algorithms and finding new quantum gate sets that will have very different properties from the ones that already exist right now. So that's pretty much what I had for today. Thank you for listening.
Fantastic. Thank you for this very interesting presentation and very nicely visualized. Everyone, feel free to ask your questions in the chat. Marcy shares, thank you for the great presentation. What will be your direct next steps, Aritra, in the next? Oh, Shashi is also coming with a question. Let me ask that first. What if we have quantum memory? Can we use it to break the barrier due to decoherence? As a result, one gate set can reach the state previously not possible. You mentioned black hole interiors. Are there papers referring to it? So what if we have quantum memory? Can we use it to break the barrier due to decoherence?
So the effect of decoherence will also be on the memory. So it's not just gate errors. There's a continuous decoherence also on the quantum memory. But if you're specifically thinking of in terms of quantum circuit complexity, there are ways to basically trade off time and memory. It's called as it comes from Charles Bennett. It's called Bennett's pebbling game. And with that, you can, if you have a lot of memory resources with much less time, you can basically trade one off with the other and implement the same amount, same computation based on what you have, what resources you have. I'm not very familiar with high energy physics and the black hole thing. So I read that article, the second law of quantum complexity, mostly from the point of view of quantum computation. Yeah, so I'll be, it will be pretty hard for me to comment on anything to do with black holes.
Yeah, one last question. Radu, please get ready in the meantime. Ray asks, in the conclusion, you mentioned quantum knowledge seeking agent. Is this similar to self-supervised learning?
So quantum knowledge seeking agent is more a quantum reinforcement learning model. So where you have a classical world, but an agent, sorry, we have a quantum environment and a classical agent is trying to model it. So it's kind of like the brain of Einstein, which let's believe it's classical, just by performing experiments, basically by performing quantum process tomography, it tries to learn what the quantum environment is. So that's basically the quantum knowledge seeking agents, and it optimizes the modeling method by using Solomon induction in the quantum setting. So it tries to make a very short code that can model, that can act as a model of the environment.
Great. Thank you very much again, Aritra.